Now that we have the basic idea of equivalence rules and their usefulness in writing formal proofs, let's look at some others. First, let's complete the picture for De Morgan's theorem. So De Morgan has two versions. The first is the negation of a conjunction is logically equivalent to the disjunction of two negations. And predictably, you've got another version, which is the negation of a disjunction is logically equivalent to the conjunction of two negations. So that gives us two different possibilities. And again, it's the negation of a conjunction, the negation of a disjunction. Avoid the temptation to think of this as a case of distribution or something along that line. Distribution is one of our equivalence rules, and it operates differently because of the operators. That's why De Morgan's basically is De Morgan's. It has its own name for that very reason. It's about the relationship between negation, conjunction, and disjunction. And the actual rule distribution behaves a little differently. All right, so that's De Morgan's theorem. Second on the list of our axioms is commutation, and we abbreviate that commutation. Incidentally, if you want the full names of these written out, consult that axiom chart that's linked to the coursework calendar. Commutation is really just about order, and it applies to only two operators, conjunction and disjunction. P or Q is logically equivalent to Q or P. It might seem like we want to add a few more operators to commutation, which is really just changing the order. But you try this for yourself. Do a truth table with what looks like commutation on material implication and see what you get. These two are demonstrably not invalid, and so or maybe I should say logically equivalent expressions on either side of this symbol, which you can prove with a truth table. And by the way, I encourage you to construct truth tables for all of these expressions and prove this for yourself, because it's really good practice for constructing truth tables. Next we have association. And so commutation is about order. Sometimes this is called the commutative property in mathematics. Association is about grouping. So as with many of these, there's two different versions of this. So let's look at P or Q or R is logically equivalent to, and then basically here, whoops, I'm missing parentheses. We're going to regroup these so that we have P or Q together or R. So notice here, P, the major operator, the rest of the expression, Q or R. Here we have P or Q, the major operator, the rest of the expression. So it's basically regrouping, and notice you have to have disjunctions all the way through for regrouping to work. Incidentally, try this for yourself. Try it with other operators. It so happens that it does work for conjunction. So what we have here is Q and R on one side, and it's logically equivalent to the regrouped version, P and Q and R. Again, here we have P, the major operator, and the rest of the expression. It's treated like a unit. Here we have P and Q, the major operator, the rest of the expression. So again, it's just a matter of regrouping. All right, let's have a look at association. I'm sorry, at distribution. This is the one we mentioned earlier. So distribution is abbreviated DIST. DIST, I accidentally wrote an R. You can use DIST. All right, so let's look at how distribution works. So look at the expression P and Q or R. Okay, so all of this is a unit, and then on the other side of our logical equivalence, we have P and Q. So the and goes to the Q first, right? Or P and R. So P goes to the R second, and the connecting operator is OR. So see, here's the connecting operator there. Connecting operator there. What's distributed in the first version is the and. The and is distributed over an or. So we end up with the and being connected by the or. Here we have an expression connected by and to a disjunction. So you could think of it as the and is being distributed over the or. Of course, the alternate form does the opposite. It's P or Q and R. And what's logically equivalent is, so let's put our parentheses for grouping, is P or Q and P or R. This is a very useful logical equivalence rule in constructing proofs. Why do you think that might be? Because if we have an expression like this and we can turn it into this, then we can use simplification to get either this part or that part. Very handy in proofs. All right, let's look at one more. This one is quite straightforward. Let's say we have an expression P. P is logically equivalent to the negation of P. This is an appropriately named equivalence. It's called double negation. Double negation is pretty obvious, but you can construct a truth table to prove to yourself that these two expressions are logically equivalent. But double negation gives us an opportunity to point out something that's important to remember. If you have P in an expression, you can substitute not P for it. And conversely, if you have not P in an expression, you can substitute P for it. So the reason that this is a double-headed sign that I've used to indicate logical equivalence is because it should remind you that you can substitute in both directions. So this can be rewritten as this, or this whole expression can be rewritten as this, depending on what you need to advance a proof. One other reminder in this, since we're talking about sort of strategy issues, is don't forget that unlike inference rules, which have premises, the schemas of which have to apply to whole lines, unlike that, the equivalence rules can be applied to whole lines or parts of lines in a proof. So let me give you a quick example of that. Let's say we have an expression not P or Q on some line in a proof, N. Then on some line below that, like N plus 1, we can write P or Q. And what we'll invoke is double negation on line N. Now, the reason this works is because this expression is one side of this logical equivalence, double negation. And so essentially we are writing something logically equivalent to it here. So this is a great example of how an equivalence rule can apply to a part of a line. How it applies to a whole line is obvious. If you have an expression like this on a line, you can rewrite it as that.